Hello everyone. In this video, we're going to use the ADC feature on the MCU board to measure the ADC value using variable register. Before we do that, we have to do the circuit configuration. For this tutorial, we're going to use the variable register, which has the three pins over here. So for the first pin, you have to connect with 3.3 voltage on the MCU board. And when it comes to the second pin, you have to connect with the pin which supports the ADC feature. In my case, I'm going to use PB0. And for the last pin, you have to connect with the ground. So that's it for the circuit configuration. Well, actually, I include the clock initialization function over here, just so you know. And so especially peak clock 2 that we're going to use for ADC is 36 megahertz right now. Before we move on to port B setting, well, if we take a look at the datasheet first, well, the GPIOB and ADC is right connected to the APB2 clock, so that's why um, well, to enable the GPIOB and ADC related clock, we have to take a look at the APB2 enabled register. And if you take a look at this table over here, well, PB0 supports the ADC feature over here. So in this video, in this tutorial, we're going to use the ADC1 and channel 8 over here. So we're going to use ADC1 and channel 8. There we go. Now let's move on to port B setting. So we're going to move on to the RCC APB2 enable register. Well, we have to enable this pin first. So I'm gonna put 1 to enable this clock. So before we do that, I'm gonna clean up this bit first. Well, so if we turn this number into hexadecimal number, it would be 8. So it would be 0, 0, 0, 0, 0, 0, 0, 0, 8. There we go. And then I'm going to enable the GPIOB clock. And after that, since we're using the PB0 pin as an analog mode, the ADC feature, so we have to turn the PB0 mode to analog mode. To do that, we have to take a look at the reference manual. So, well, when it comes to analog mode in input mode, because we're going to read the variable register value with the analog mode in input mode. So the mode bits should be 0, 0, and analog mode as well should be 0, 0 in input mode. So I'm gonna use the bit conversion operation and AND operation to clear up this part to make those 4 bits 0. So it should be F. So in this case, 0, 0, 0, 0, 0, 0, 0, F. There we go. Let's now move on to step 2, which is ADC configuration. So since the peak clock 2 is related to ADC, so we have to control the APB2 enable register again to enable the ADC clock. So if you take a look at this reference manual over here, I'm gonna enable this clock. But before we do that, I'm gonna clear up this part, which is bit 9. So I'm gonna use the bit conversion operation. So I have to left shift 9 times to clear up this part. And after that, I'm going to enable the ADC clock like this. And so, but what I'm trying to say right now is, well, if you take a look at this explanation over here, well, ADC input clock is generated from the P clock 2 clock divided by a prescaler, and it must not exceed 14 megahertz. But our P clock 2 is right now 36 megahertz, but you know, it must not exceed 14 megahertz. So I'm gonna divide uh, this number by 4. So I'm gonna make the ADC input clock to 9 megahertz, which is much lower than 14 megahertz. And so, yeah, we have to set the prescaler using the configuration register. So if you take a look at this part, we have to set 0, 1 to divide by 4. So before I'm gonna do that, I'm gonna clear up this part first. So it's gonna be 1100. If I transform this number into hexadecimal number, it will be C. So since I'm using the AND operation and bit conversion operation, it's gonna be 0000 C 000. And then I'm gonna put the number, which is 0100. This is one chunk. So if I turn this number into hexadecimal number again, it will be 4. So the entire number will be 0000400. There we go. It's gonna be 0000400. There we go. Now let's move on to step 3, which is extra ADC configuration. And just keep in mind that we're going to use the channel 8 with ADC 1. And in this register, I'm going to enable the software start feature because we're not going to use the injected group. We're just going to use the regular channel. And I'm going to turn on the AD converter for the first time. And I'm going to set the single conversion mode in this register. So if you take a look at the register over here, we have to enable the software start feature in this part. And I'm just gonna select the single conversion mode in this beat. And I'm gonna turn on the AD converter with this beat. And so, well, at this point, I'm going to use the software start feature. So I have to put 111 in this part. And to make the single conversion mode, over here, I have to put 0 in bit 1. So it should be 0 over here. And I have to put 1 at bit 0 to enable uh, the AD converter. So this bit should be 1. So, well, if I turn this number into hexadecimal number, it would be E, because this 4 bits is one chunk. And if I turn these bits into hexadecimal number again, it will be 1. For the convenience, I'm gonna use the equation operation with this register. So the entire number would be 0, 0, 0, E 0, 0, 0, 1. There we go. So it's gonna be 0, 0, 0, E 0, 0, 0, 1 with equation operation. And let's take a look at this register over here. So if you take a look at this register, well, we have to set the cycle for the sample time selection. Since we are going to use the channel 8 over here, and well, the ADC is pretty slow for the processing, so I'm gonna make longer for the sampling time. So I'm gonna put 101 over here to make the 55.5 cycles. So, well, since the reset value is 0 in this case, so I'm just gonna put this number right away. So this is one chunk, this is one chunk. So if I turn this number into hexadecimal number, it will be 5. So the entire number would be 0, 5, 0, 0, 0, 0, 0, 0. There we go. So this is gonna be 0, 5, 0, 0, 0, 0, 0, 0. There we go. Well, since we are using the channel 8 only, so our mode is single channel mode. So to make sure with that mode, well, if you take a look at this part, the reset value is 0. So, well, this L bit is the regular channel sequence length, but in this case, our length is just only 1 because we're just using channel 8 only. So we don't really need to change this number at all. So I'm not gonna write down the code here, the extra code here, and after that, we're going to write down the channel number over here. So the SQ1 stands for the first conversion in regular sequence. So we have to put channel 8, the number 8 in this 5 beats. So if we transform, we don't really need to transform this number into beats. Well, we just write it down right away. And so, but before we do that, I'm just gonna clear up this part first. So this must be 1, 1, 1, 1, 1. So this is one chunk. So it must be F, and this one chunk would be 1. So I'm gonna put 1F using bit conversion operation and AND operation to clear up this part first. So it's gonna be 0, 0, 0, 0, 0, 0, 1F. There we go. And after that, I'm going to put the number over here, 0, 0, 0, 0, 0, 0, 0, which is our channel number. Well, let's move on to the last step, which is conversion procedure. I'm just gonna introduce this procedure just for real quick. First of all, we have to set the AD on beat to 1. And after that, we have to enable the software start beat. And then we have to check the end of conversion bit to check whether the ADC is done or not. And after that, we're gonna read the data register so that the end of conversion bit is automatically cleared. And so first of all, we have to enable the AD on bit. Well, if you take a look at this part, well, conversion starts when this bit holds a value of 1 and a 1 is written to it. Well, this is the first condition, and this is the second condition to launch the AD conversion. So we did this in line number 105 over here, but according to this reference manual, this beat, AD on beat, should be enabled at least twice. So I'm just gonna relaunch the AD converter again, since this beat is beat 0. So I'm just gonna put 0, 0, 0, 0, 0, 0, 0, 1. Sorry. 0, 0, 0, 0, 0, 0, 0, 1. There we go. Well, I have to enable the software start bit, because which means that actually the software start bits is the actual beginning of the conversion of the regular channels. So I have to put the number 1 over here. So if I transform this number into hexadecimal number, it will be 0040. So 00400000. There we go. Well, the reason why I separate these two code, even if these are the same register, is because of this explanation over here. Well, if any other bit in this register apart from AD on is changed at the same time, then conversion is not triggered. So because of this explanation, if I combine these two code, then it might malfunction because of this reason. So that's why I just separate uh, these two code like this. Now I'm gonna wait until the end of conversion beat is set. So if we take a look at this reference manual over here, 1 means that the conversion complete. So I'm gonna use the AND operation to check this bit. So it must be 2. If I transform this number into a hexadecimal number, it will be 2. And so 0, 0, 0, 0, 0, 0, 0, 2. There we go. And if the result of this operation is 2, which means that it is the end of the conversion. And so 2 and 0 is different. So the entire of this operation, the entire result of this operation is false. So we are qualified, we are allowed to move on to the next part. So this is the right code. Well, now we're gonna read the data register to measure the ADC value from the variable register. But the other reason why we have to read the data register is to clear the end of conversion bit. So if you take a look at this part, this bit is cleared by software or by reading the ADC data register. Well, the reason why we have to clear this bit is because we have to, convert the ADC value over and over. And so this code is very important. And after that, if our value is measured, then we're going to calculate the real voltage over here. And so this is all about the code. So I'm gonna build this project. Well, build is completed. Well, I just unloaded the code right now. So as I rotate the potentiometer, the ADC value and the corresponding voltage change as expected. And so, well, the reading reaches 0 at the minimum, but it doesn't fully reach 3.3 volts or 4095 at the maximum. This is normal in real hardware situation due to imperfect reference voltage and small analog errors. Well, this is all about today's tutorial, and I hope you find it very useful through this video. See you on my next video. Bye guys.